lesson 2, so applications of prime factors, so we're building on yesterday's. So the review, express numbers 48 and 72 is product of prime factors. So what that means is we're doing the tree from the warm-up. Okay, so let's just do that together really quickly just to kind of get in the rhythm. So if I'm breaking down 48, sorry, it's going to take a picture every time when I'm writing on it. I'll turn the sound down in a second here. Okay, so 48 we can break down to, I got 4 and 12, 2 and 2, 4 and 3, 2 and 2. So here's your prime factors of 48. Okay, remember I can write that as 2 to the 4th times 3, or I can write all the 2's out times the 3. 72, just right over here, so I have a little bit of room. 36 times 2, 6 times 6, 3 times 2, 3 times 2. So we have, these are our prime factors. So we have 3 2's and 2 3's. It's kind of confusing, but that's what it is. Okay, so like right now, again, even though this is being recorded, and I'm recording right now, once I'm telling you this, you guys still ask questions. We can still stop. It's not like we can't talk, okay? So just treat this like a normal lesson and no problems with that, okay? All right, so greatest common factor is a set of whole numbers, the largest whole number that goes into that number, okay? So for example, the GCF of 8, 16, and 20, what's the biggest number that goes into all 3 of them? Lauren? 4, right? So we would say 4 here. That's the greatest common factor of all those. Okay, I'll move this up here. All right, where are we at here? 790. Okay, so there we go. Okay, so we have the one at the top there. Gotcha, I gotcha. I'm skipping a section. That's the problem. There we go. Okay. All right, so we have 8, 16, 20, which is 4, so we're good with that. So then what is the greatest common factor of these sets? So 15, 25, and 35? 5. Okay. 18 and 20? 2. Yeah, 2 is only 1. And then 36 and 54? 9. Good. No. 18. 18 actually goes into both of them. Tricky. 9 does go in both of them, but not the greatest one. So that's okay. Okay, in cases like this, we can use prime factorization to determine what their biggest common factor is. Okay, so for example, GCF of 48 and 72, like what they've done is they've taken what they have in common. So here, this is what we got for 48. And here's what we got for 72. Well, they have a 2 in common. They have a 2 in common. They have another 2 in common. And they have 1 3 in common. That's why they've written 3 2's and a 3. So that number will be their greatest common factor. 2 times 2 is 4, times 2 is 8, times 3 is 24. 24 is their greatest common factor. That's the exact prime factors they share. Does that make sense? The exact prime factors they share. So prime factors is the stuff on the ends from the top. Okay, so 24. 24 times 2 is 48, and 24 times 3 is 72. Okay, questions there? Okay. All right, so use prime factorization to determine the greatest common factor for the given whole numbers. So they want you to do it this way, okay, to kind of see what they're talking about. So I'm going to go 9 times 10, and I'm going to go 3 times 3, and 2 times 5. That's where I'm going to stop for 90. Then I'm going to do 225. I'm going to do 225 is a little bit over here more. So 225 is 15 times 15. 5 times 3, and 5 times 3. Wow, it's a horrible 3. So, what do they have in common? So we go through here. So they have, let's see, a 5, a 3. You said 2 3s, a 3 and a 3, a 3 and a 3, and they both have a 5. Okay, so that means that their greatest common factor is going to be 3 times 3 times 5, which is 45. So 45 is the GCF for 225 and 90. Okay, 154. So if we do 154, we're going 2 and 77, 7 and 11 is all for 154. 198, 6 and 33, 3 and 2, 3 and 11. Okay, so then we go through here. Let's try to figure out what do they have in common. So they got a 2, not a 7, and 11, right? So just 2 and 11. So if it's just 2 and 11, that's simply 2 times 11. So 22 is our greatest common factor here. Okay, questions there? So far, so good? All right. All right, so an example 3 here says use prime factorization to determine the greatest common factor of the given whole numbers. So now it's giving us kind of a bigger group. So you can do a couple things. Okay, you can either use a tree, you can do a division table, whichever you want. It doesn't really matter to me. I think the division table might be a little bit easier because it doesn't take as much space. But if you like the tree better, you could do the tree. So on my notes here, I'm going to go with a table because that's what they have. So 245. Okay, the first thing to divide it by was 5. 245 divided by 5 is 49. Divide that by 7, you get 7. Divide that by 7, you get the 1. So 5, 7, and 7 is the prime factorization of 245. If you're wondering how I'm getting those things, like remember, always look first, is it even? If it's even, divide by 2. And then this one ended in a 5. So I divided by 5 because it ends in a 5. Okay, so that's how you kind of figure out where to start. It doesn't matter if you try to 7 first or whatever, but I just know I'm not going to do an even, right? It's an odd number. So same thing for 315. I'll divide 315, I don't know, whatever I really want, but my notes has a 3. I probably would have done a 5, but my notes has a 3, so I'll just do a 3. So 315 divided by 3 is 105. 105 divided by 3 again is 90, so 35. Divide that by 5 is 7. Divide by 7, that's a 1. So 3, 3, 5, 7 for that one. And the last one here, I'll just kind of do it on the bottom so I can save some space for the part B. 770. First thing I would probably do it by, you can do it by a 2, because it's even. Okay, that kicks out 385. Then I can go by 5. Okay. And then from there, we have 77. Okay, and then so that would be a 7 there, 11, 11, 1. All right, so now we're looking at these sections each. We're looking here, looking here, we're looking here for similarities. Okay, so if I go through there and I want to pinpoint, okay, they all have a 5. Okay, so write the 5 down. They all have a 7. Okay, so write the 7 down. And that's all they have, because this one only has a 7 left. This doesn't have another 7, so that's it. So the greatest common factor is what? 5 times 7. So 35. Don't jump the gun there, Ollie. Okay. Okay, I'll give you a second here to go ahead. I want you to try part B on your own, and then we'll go over in a second here. All right, so let's take a look here. So 171, you could have broken it down differently. I'm just going to go with my notes so we can just kind of get through a little quicker. So 171, started with a 3, went to 57, did another 3, went to 19, did 19, and that was a 1 because 19's prime, right? Correct. There we go. There's my support. Okay, 285. Okay, we do 285. You divide that by 3. Again, you could have done 5 first if you wanted. Okay, I got 95. 5. 19 again. Okay. And down here, 399. 399 started with a 3. Then went to 7 because it was 133. Then I got 19 again. Seeing the pattern here. They obviously want us to have 19 as our number. And 1140. So 1140 started with a 2. Got 570. Did another 2. Got the 285. And from 285, we already know what's the rest. We can just steal it from there. It's going to be a 3. It's going to be a 5. It's going to be a 19. Okay, so now we'll go through and we'll look and we'll see where they match. Well, we kind of already saw the idea that the 19s are going to match. Does anything else match? 3, good. That's it, huh? 1 always matches. That boy. Okay, so then 3 times 19 is our greatest common factor. So 3 times 19 is going to give us 57. So 57 will be our GCF for that example there. Okay, you guys get the number pattern there? Making sense? Okay, all right, cool. All right, so now we're going to switch gears from greatest common factor to lowest common multiple. So instead of finding the biggest number that goes into both, we're going to find where the two numbers meet first. So the lowest thing they go into together. That's what lowest common multiple means. Okay, so look here. So multiples of 6 are 6, 12, 18, 24, 30, 36, 42, 48. Multiples 8, 8, 16, 24, 32, 40, 48, and 5. Their least common multiple is 24, correct. Here, sorry, there, and there. That's their least common multiple. Okay. Any questions with that? So make sure people get confused on greatest common factor versus least common multiple. Okay, think about multiple, you're going forward. Where do they meet? Forward. Factor is inside, underneath, okay? Think about it that way if you'd like. Okay, all right, so let's get down here. All right, so state the lowest common multiples of the following: 5 and 7, 10, 15, 20, 10, 12, and 14. See how you guys can do on this one on your own first, and then we'll go from there. Or what'd you get for A, Noah? Didn't get it? Okay. So where does 5 and 7 meet? Yeah. 35, right? So a lot of times you can multiply them by each other. They're going to for sure meet there because they both, that's what they multiplied to get there, right? But you can see the pattern. Sometimes they meet earlier. Okay, so 5 times 7 is 35, and that turns out to be where they meet. So 35 is correct there. Whoops, not highlighter. 35 is correct there, which is good. Okay, Josie, did you get B? Yeah. Where do they meet? 60. Okay, good. So again, you just are looking at the patterns of what these numbers are doing. So 5 goes 5, 10, 15, 20, 25, 30, 35. 7 goes 7, 14, 21, 28, 35. So you see 35 is the first time they matched. Here, 10, 20, 30, 40, 50, 60, 15, 30, 45, 60, 20, 40, 60. So you'll see that they meet at 60 again. Rather than me writing all these out for you, just kind of doing it out loud. Okay, 10, 12, 14. Denise, did you get that one? Didn't get that one? Anybody get that one? The second B? Luke? 420. Okay, good. That's correct. And how did you do that, Luke? Okay, so what did it say below? Good job. Okay, so it says C was more complicated. Prime factors can be used to simplify the solution. So we know that 10 is 2 and 5. Okay, we know that 12 has 2, 2, and 3. And then 14 is 2 and 7. So to determine the least common multiple, take all the prime factors of one of the numbers and multiply it by any additional factors in the other numbers. So what they're saying is so they took the 2 and the 5. They took this guy. Okay, now this one has an extra 2, right? So like this one's already done. We need this one, so they added that. We need this, so they added that. We don't need that 2. We already have that single 2. We added the 7. Those numbers multiplied was the least common multiple. So like no repeats. Does that make sense? So they all shared 2 and 5. So we have 1, 2. This one we had 2 2s, so we had to add another one. Okay, this one only had 1, so we'd have to add 1. That's the difference. Everybody understand that? That's the most confusing part there is the overlap of those 2's. Okay, so then that's how Luke followed the directions. Okay, and he got 420. Okay. All right. Next piece. Very good, very good. All right. So this one. Example 5. Use prime factorization to determine the lowest common multiple. So if we're doing this one, 15 breaks down to 5 and 3. 35 is 7 and 5. So what would you write? Well, they share a 5, correct? So just 1 5, a 3, and a 7. That's what you would write. So that's the least common multiple for them. 15 times 7, so it would be 105. Yeah. If they match, correct. Yeah, if they match. Okay, so then like 126, I'll break this one down. 2, 63, 7, 9, 3, and 3. So 2, 7, 3, 3 for the first one. 441, I'll break that one down. 441, I have 3, 147, 3 and 49, 7 and 7. Okay, so we don't want any repeats. So we go to here. So we have a 3 and a 3, a 3 and a 3. So they both have 2 3s. So do I put 1 3 or 2? 2, good job. 3 times 3. Okay, they both share a 7. So I have 1 7. What's left over? A 2 and a 7. Do I put those? Yes, we put those as well. Okay, so what they share, you don't double. What they don't share needs to be accounted for. Okay, so they shared 3 and a 3, 3 and a 3. They shared a 7 and a 7, a 7. They didn't have this shared, so it has to be by itself. They didn't have this one shared, it has to be by itself. So you should get 882 for this one. Questions, concerns? Okay. All right. Go ahead and try C. I'll pause the video. Try C. You have 3 of them now. Okay. So you're gonna have to. That means if they all have a 2, then that counts as 1 2. Okay. All right. All right. So then we're breaking all three of these down. So 22, we have 2 and 11. That's all we have there. Okay, and then 154, I'll kind of do that over here. 2 and 77. And then we get that 7-11 combo again. And then 198. Be 2 times 99. 9, it's all right, I can still do that. And then 3 times 3. All right, so this is where we go back, and so we say, okay, they all have a 2 in common. So that's done. 2. They all have an 11 in common. So that's done. So that's done for 22. 7, no 7 here, so I need to write a 7. And a 3 and a 3. So that's what's left over here. So 2, 11, 7, 3, and 3. When you multiply those out, you get 1386 is the least common multiple. Okay? All right, so then prime factorization of perfect squares moving forward. So what is a perfect square? Does anybody know? Top hand? Perfect square, what is that?
Number that has a square root.
Correct, a whole square root. Yeah, Luke? Right, number that's created by multiplying a number by itself. So 5 times 5, 25 is a perfect square. 10 times 10, 100 is a perfect square. Okay, that's where that comes from. That's all correct. Okay. It's going to drive me nuts. I got to get this fixed. All right. Should be far enough there. So they have, so perfect squares, the whole numbers include 1, 4, 9, 16, 25, 36, 49. This line up here. Every perfect square has 2 square roots, 1 positive and 1 negative. So that just means that 5 squared is 25, negative 5 squared is 25, because a negative times itself is a positive. Okay, so when you're doing square roots, just understand there's a positive side and a negative side. You really need to know that for Math 20. When we do our parabolas, you have to think about the negative answer and the positive answer all the time. So keep that in mind. Okay, the principal square root of each number above is 1, 2, 3, 4. So 1 squared is 1, so the principal square root is 1, etc. In this lesson, we are dealing with the whole numbers. We'll use the term square root to mean the principal square root. So complete the prime factorization of the following perfect squares. So 9, we just complete that just to 3 times 3. That's as far as we can go. The square root of 9 is 3. Because it's a pair of 3s. Number times itself, like Luke said. So 36 is 4 times 9. Okay. 2 times 2 and 3 times 3. So what you want to notice is that we have 2 pairs of 2 times 3. Right? We have 2 of these. Well, what's 2 times 3? Well, that's 6. 6 times 6 is the perfect square there. Okay. 49, can only break it down one way. 7 times 7. So that one breaks down to 7. The square root of 64 is, so this one you're going to see it's going to be a pattern. So we got to go 8 times 8, 4 times 2, 2 and 2, 4 times 2, 2 and 2. So I have 6 2s. So you want to think about them in groups. So what groups do we have? We have 1, 2, 3 groups of 2. So that means I want to go no, it's writing yellow for right now. That means it's 8. 2 times 2 times 2. We had 3 groups of 2's, which equates to 8. Take my pens off is why. Okay. Okay, continuing here. Almost done. All right, so we got these two here. So it says consider the number 44,100. Use a calculator to find the square root. So everybody do that in the calculator now if you'd like. Okay, what do we get? 210. Good. So in our calculator we got 210. And then it says explain how we can use the prime factorization of 44,100 to show that 44,100 is a perfect square. So verify your calculator. So how they be a perfect square is they have to have, notice were completely rounded. What I mean by that was 49 was 7 and 7. 64 was 6 2's. So they are all paired up because they're perfect squares. So we can show this if 44,100 breaks down to perfect pairs. Does that make sense? So we're going to go ahead and do that now. So it's going to be a little bit, I don't want to say tedious, but it's going to be a big number here. So we got this. So we break that down. They started with 100 times 441. We know that's 10 and 10. We know that's 5 and 2. 441 breaks down to 9 and 49. 3 and 3, 7 and 7. So if you look at this, I have 2 5's, I have 2 2's, 2 3's, and 2 7's. I have 2 of everything. So it's a perfect, all of them are perfect pairs, therefore we just proved that is a perfect square. Okay, so you guys go ahead and try example 7 here. You're going to see if 1225 and 3042 are perfect squares by showing prime factorization. So show me the pairs of those. Okay. 1225 and 3042. I'm going to move it up for you a bit. All right, so let's look at these here. So 1225. So 1225 can break down to, I have, whoops. So we have 5 and 245. That breaks down to 5 and 49, 7 and 7. So if you look, we have pair, pair. So it's a perfect square. Okay? So as long as you have an even amount of pairs that they match up, 2 5's, 2 7's is a perfect square. Okay, just finish up what you were talking about, Ollie. Okay, so in this one, 3042, 2, 15, 21, 3, 507, 3, 169, and then 13 and 13. So if we go through here, okay, we got 3, 3, cool. 13, 13, cool. 2's by himself. Not a perfect square. So then what would you know, like, what's another way you can know right away it's not a perfect square? It's another way, just by looking at the branches. If you have 7 branches, can it be a perfect square? No, it has to be even number of branches, right? 1, 2, 3, 4. Okay, there's a chance. 1, 2, 3, 4, 5. Not a chance. I can't pair up 5 numbers. Okay? So odd number, even number of branches can help give it away as well. Okay? All right, so prime factor, so cubes now. So what do you think is going to change for cubes? Not pairs of 2, but pairs of 3. Because cube, right? Cubic means 3, 3-dimensional, if you don't know that. Cube comes from 3-dimensional. Okay? So 27, does it have any perfect cubes? Well, let's see. 27 breaks down to 3 times what? 9. Very good. And then that's 3 and 3. How many 3's do I have?
3.
So is it a perfect cube? Yes. Okay, 216. 6 and 36. 6 and 6. 1, 2, 3. Yes. We're looking for groups of 3 now. 3,375. So 5 and 675. 5 and 135. 5 and 27. Oh, I'm running out of room. 3 and 9, and then we have right over here 3 and 3. So we have 3 3's and 3 5's. So yeah, that's also cubic. 2 sets of 3. 3 5's, 3 3's. Okay, and on to our last example here. All right. Okay, last piece. Prime factorization of a perfect cube will involve sets of factors which each occur 3 times or multiple of 3 times. So that's what we talked about, groups of 3. If the prime factorization of a number does not result in factors which they occur 3 times, then it's not a perfect cube. Okay, same thing as the perfect square, except for a perfect square was 2. In each case, use prime factorization or division table, however you want to do it, determine whether number is a perfect cube. So we're just seeing if these are. So they have division tables, so we'll just go ahead and do one here.